What up, people? Hope you guys are doing well. Let's jump on getting to our OneNote and doing our review of where we were last time when we were looking at example 2.4. So here we are. So what you're seeing here is that you're seeing that I have a circuit, and then we identified 4 different colors, which tells me that I have 4 nodes. From these 4 nodes, I then start to look at what is in parallel, what's in series. If it's in parallel, then they share 2 of the same colors. If they're in series, they only have 1 color in between resistors. So what we see here is that between the red and the black node, I have the 6 and the 12, which tells me immediately that that's a 4K resistor. And then I have between the violet and the black, I have the 4 and the 12. Since that's a third, I divide by 4, it gives me a 3K. I said a 3 ohm, but it should be a 3K. So then if I go and I reduce my circuit, what do I mean by reduce my circuit? I go in and I redraw this thing. What do I see here? Well, what I see here is that I now have, between my violet and my black, I've reduced it to a 3K, and between the red and my black, I have a 4K. So now, what we're looking at here is that our goal here was to do what? Was to solve for the current I0. And what we're doing here is that by looking at this resistor reduction, I'm converting, right? I'm converting my I0 calculation into a voltage V3 calculation. So my goal now is not to calculate I0, is to calculate V3. So what you're going to see here is that I'm going to go through a series of steps to try to reduce how I do this here. Now, what I'm going to do here is that still the circuit is somewhat complicated. And so what I want to do here is that I want to reduce it as simple as possible, but not any simpler. That is, if I look at this thing here, I could see that between the 9K and the 3K, they're in series. So what do? I do one further reduction here. So then I go from, since 9 and 3 are in series, it's a 12K. But then note that the 4K is what? So let's be careful here. So that means here, I now have a voltage across these guys here. And look at my notation here. When I look at that voltage, note that the 12K and the 4K are in series. And when I go and I look at this thing, I could see that the voltage across this 3K here, as I reduce it one more time, must divide that 12K, that 12 volt, into 6 volts across each of the resistors. So could I reduce this more by making this one 6K resistor? Yes, but we don't want to do that. So now what I'm going to do here is that now that I have the voltage across this 3K here, right? Now that we have a voltage across the 3K, and what I mean by that, I'm talking about this purple 3K, which is 6 volts. I now uncompress the circuit. In other words, I'm now going to work my way back again to where I was. So check it out. You're going to see here is that, what does this tell me here? So what I really have is I have this sub-circuit, which has this voltage. So what do? I now re-expand this thing. And when I re-expand this thing, what do I really see here? What I really see here is that this is really what? This is really the voltage across what? The 9 plus 3, 12K. And of course, this is still 6 volts. But how did I get that 12K? Well, I go back here and you could see these guys were in series here. So when these guys are in series, that means I'm going to keep going back. And as I keep going back, what I find here is that this is really this guy. This is my 9K, this is my 3K. And I know that this guy is 6 volts. But remember, we want the voltage across the 3K, right? That was our goal. So if I come back, you could see that we're really looking for this voltage right here. So what am I going to use? I'm going to use VDR to get the voltage, the blue voltage, V3. So here I go. So then that means here, V3 is then going to be equal to what? Its resistance divided by the sum of them times its branch voltage. In this case, it's got to be the 6 volts. So you can see here that when I do that, I'm going to get 18 divided by 12, 18 divided by 12. I believe that's 1/2, right? That's 3/2 volts. So now I have my voltage across 3 here, right? But that's not what I'm after. What am I after? I'm after the current. So keep stepping back. So here's where we're at now. So now I got the blues 3. And if I keep going back, I want this current right here. So how did I get that 3? So let's focus on that. So then I now focus on the 3K resistor. So if I look at this thing, what I really see is that this 3K, which now has a voltage, V3, which is 1.5 volts, I really find that this is the resistor of what? And if I go back up, you could see here, it's the 4 parallel to the 12. So when I look at this, this is really the 4K parallel to the 12K. So that means here that I really have this guy. So here's my 4K, here's my 12K. And if you look at the circuit here, you could see that the current is across the 4, is through the 4K. So now, here I go. I know now that this guy is I0. That's what we're after. But I know the voltage across this thing. The voltage across this guy is 3/2 volts. So now what do? I apply Ohm's law to get I0. So I could see then that the current of the 4K is what has been defined as I0. So according to Ohm's law, it's going to be the voltage of the 4K divided by the 4K. So this is going to give me 3/2 divided by 4. And in this case, you could see here it's going to be 3/8 milliamps. And that's I0 right there. And I believe that's all that that question was asking. They're just asking, determine I0 in the circuit, which I did. Okay, I'm going to go to the next circuit now. Let me grab that. And here we go. So you can see there's a lot more resistors in this circuit. So here's what I want you to do. Go define the nodes. Go color them in. Let me give you 30 seconds or so to tell me the number of nodes. Okay, let's do it. So let's look at the number of nodes. So that means I'm looking for equipotentials. So here's my first one here. I'm going to use my red color. Nope, not there. Okay, so that's a fairly big node. Let's go to the second node. I'm going to choose green for my second node. And then finally, I'm going to have my third node, which is right here. So what you're seeing here is that I have 3 colors implies 3 nodes. So the fact that I have so many resistors with only 3 nodes tells you immediately that a lot of stuff is in series and parallel. In this case, it has to be parallel. So to be a little bit more systematic here, I'm going to define this as node 1. Instead of calling it red, I'm going to call this node 2. And so what you're seeing here is that I'm going to focus on those 2 nodes right now. The fact that I have all of these reds connected to these greens, so anything between the green and the red must be parallel. So let's look at these. So what you're seeing here is, look at that. That guy's in parallel. 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 So there are 5 resistors that are in parallel. Why are they in parallel? Because they share 2 nodes that are similar. So what we're finding here is that there are 5 resistors in parallel between nodes 1 and 2. So let's go look at this thing here. So that immediately tells me the following thing here. So that means I'm going to look at the R parallel resistance between nodes 1 and 2. So what does that mean? It really means this here. It means that this guy has to be, so I have 12, parallel to 12, parallel to 12, parallel to 12, parallel to 3. And so when I look at this thing, what this really tells me here is that this has, so the 12 resistor, there are 4 of them, plus one of them is 3. And so when I calculate that number, you could see here that this has to be 2/3. In other words, the resistance between nodes 1 and 2 is 1.5 ohms. Okay, so look at that. I reduced this. I'm going to reduce this very, very quickly. So the question is now, how do we redraw the circuit? And the best way to do that is pick one resistor. Now, I would not pick the 3 ohm resistor. I would pick these 12 ohm resistors. Okay, I could pick the 3, but it's going to be easier to only focus on the 12s here. So what you're going to see me do here is that, look what I'm going to do here. I'm going to focus on this guy right here. So I'm going to focus on this 12 right here. Okay, so I'm picking 1. So what I can do here is that I can take the 1, 2, 3, and 5 resistors and combine it into the 12. Okay, and combine it into the 12. And when I do that, note that this end right here, okay, I'm talking about this point here, all of those resistors, that is this resistor right here, I'm going to replace it with the 12 ohm resistor 4. So if I do that, look how I draw this now. So I have my current source. I'm going to have to, so let's look at the current source here. Here's my 6 amp current source. So look what I'm going to do now. I'm going to come in here and I'm now reducing this guy to the resistor 1, 2. So you might be saying, but wait a minute, what about that red line? But remember, that red line at that black dot, they're all the same. So there is nothing above this now. It's all going down R2. And then look what happens here. Look at my path now. So what I'm going to do here is that now I'm going to go along this direction. As I go along this direction, note that the 3 resistor 5 here is connected to the red and the green. But that guy is gone now. Why? Because I folded it in to the R12. So then I come around and then I'm going to draw what? Here's my 3K now, or my 3 ohm resistor. And then what do? I'm going to head up this way. And as I head up here, note that I get the purple node. Here's where the purple node is at, right here. Right? I get the purple node right here. And as I get the purple node, what you're seeing here is that this guy then comes in, oops, bad color, and it connects right there to the purple node. And then what you're seeing here is that, look at the 12 and the 6 here. So if I call that node 1 and this node 2, I'm going to call this node 3. And you could see here that at node 3, I have 6 and 12 parallel. But so that means I'm going to combine these 2 resistors. So as I combine these 2 resistors, what do I actually see here? Well, the first thing that I see here is that note that the current source, the 12 and the 6 are in parallel. So in other words, you know what? I should have done this a little bit different. Let me bring this down a little bit. And I think I have to address everything in parallel to 1 and 3 first. So now let me say this. So I'm going to focus on elements between nodes 1 and 3. And what you're seeing here is that in this node here, you're seeing that between the red and violet, there are 3 parallel elements. In other words, what I'm really seeing here is that I'm seeing that the current source, the resistor 12 and the resistor 6 are all in parallel. Why? Because they have a red node and they have a violet node. So when I go to try to draw the rest of this thing, there's a couple of ways that we can draw this thing. So if I ask the question again, how do I redraw this? So now if I add that next element right here, how do I redraw this thing here? What I have to do here is that you can see that the 6 amp and the 12 and 6 are in parallel. So I could come up here and draw this like this. So that this is my 12 and this is my 6. And so how do I draw this thing? I mean, you could keep it exactly like this. And what you're seeing here is that now I can then start putting in my numbers. But before we do that, which current are we actually looking for? We're looking for the current of the 6 ohm resistor. So if I look at that current of the 6 ohm resistor, that current, look how it's going here. So you can see that the current's going this way, and it looks like the current I0 seems to be going in the same direction as this guy. So the current that we're looking for, unfortunately, I gotta bring this down a little bit more. So the current that I'm looking at is the current in this direction right here. This is what we're calling I0 right there. So now I'm gonna keep reducing this thing here. So I know that this guy was equal to what? 1.5 ohms. And so what you're seeing here is that, note that resistor, when you're looking at the resistor, this is the violet node right here. And then the other node is the red node. So the green node is now gone. Right now, the green node is between where? Let's see, the red node is right here. And the green node is right between these guys right there. So one of the things that you could see here is that I can reduce the R12 resistor and the 3, and note that the 12. So note that we can do a resistor reduction. But
Carlos, I think I'm unclear on your subscript notation for R12. What is that referring to?
these two nodes, the resistance between node 1 and 2.
Oh, huh. Okay.
And this is what I defined it as right here.
Mm-hmm.
So
in other words, it's not a reference to specific resistors that were combined.
that
It
combined
is a reference to
right.
the nodes
Yes.
that were bridged with those resistors.
Right, which I just combined into to get this 1.5 ohm resistor. So if I come back here, so note that we can do a resistor reduction, but do not include the 6 ohm resistor. Why? Then if the reason why is that you lose all the information for the current. So what we want to do here is that our resistor reduction, if you look at this, note that resistor 1, 2, and the 3 ohm are in series. So this is really 1.5 times 3. This is really a 4.5 ohm resistor. And then this 4.5 ohm resistor is parallel to the 12. So what you're seeing here is that when we talk about resistor reduction, we really have 12 parallel to 4.5. Now, what is that resistor value? Well, it has to be what? 12 times 4.5, 12 plus 4.5. And if you punch this into your calculator, you should get 3.3 ohms. So now if I redraw my circuit, what am I seeing here? What I'm seeing here is I'm seeing this. I'm going to combine this guy with these guys right there. So now if I look at my circuit here, so now I do a redraw. And so I have my current source. And now I'm going to combine it so that it looks like I'm going to take it and swing it over to where the 12 is. And then I have one resistor now. What resistor is this guy? This is the 3.3 ohm. And now I have the 6 ohm here. And I know that this guy is the current I'm trying to solve for. So now what I have is I have two resistors in parallel. So that means I'm going to use CDR to get the current across the 6 ohm resistor, which is the current I naught. So the first thing that you're seeing here is that look at the flow of the current. The current is coming from in this direction. And then you could see that when it splits, part of it goes here and part of it goes in that direction. The fact that the I naught is in the opposite direction, I have to include a negative sign. And I'm going to do that by hand. So here I go. So I naught is going to be what? I have my minus sign because it's flowing in the opposite direction. And now here I go. It's the opposite current, the opposite resistance, which is 3.3 divided by the sum of the two, 3.3 plus 6 times my branch or my source current in this case, which is 6 amps. So if you punch this in, what am I going to get? I'm going to get a value of 2.1 amps. Okay, let me be careful here. Minus 2.1 amps, and that gives me the current I naught. Do I take my minus sign serious? I guarantee you, if you mess up on the minus sign and you don't put it down, I immediately take off 1 point, even if it's a 5-point problem or even a 2-point problem. You gotta handle the minus signs. It's super, super important. Okay, now we're gonna move to the next stage. And what we're doing here is that we have now finished circuits that primarily focus on resistor reduction. In all of these calculations, did I ever use KVL or KCL? If I did, it was bare minimum. So when you take the quiz next week, the one thing you want to remember here is that you're going to get one circuit that's primarily, almost exclusively, resistor reduction with KVL, with VDR and CDR. Okay, that's what you're going to do then. If I start to grade your quiz and I find that you're using KVL and KCL on the circuits, then I know that you didn't put your time in. Then you're going to get a second question on the quiz. And the second question is one of the most important things that we're going to deal with in this course. And we're going to talk about dependent sources that primarily will require use of KVL and KCL. And that typically means that you're going to set up a system of equations. So let's go do that. So what we want to focus on now is we want to talk about dependent sources. In simple circuits. So here we go. So what you're going to find here is that now we're going to include dependent sources in a circuit. And what I'm going to do here is that I'm going to give you a series of steps. And what you're going to find here is that these steps, as always, are suggestions. It's a good pattern of thinking of how to actually solve these things. So what we want to do here is that I want to outline this process, and then I want to show you this process. Some of this process will probably be easier to do it in a different way, but I'm going to stick to this process because this is what you're going to primarily see from me. So let's go do this here. So here's our problem solving strategies for dependent sources. So the first thing that you want to do here is that when you look at the circuit, you want to apply simple circuit techniques just like you would have been doing up to this point. So you apply simple techniques treating the dependent source like any other source. So you treat it as an independent source. And then I have my own language. If you Google this, you're not going to find this language. But it's a systematic way of you and I communicating with each other. Then I say, do the following thing. Apply the dependent source condition. And typically, the way what I really call this, I call this the DC, the dependent condition. And so there's typically a two-step process here. So the first thing that you want to do here is that you want to go into the circuit and find the controlling element and see how it's defined. So that means look for the controlling element in the circuit and see how it's defined. In the beginning, you're going to see that it's going to be quite easy. And the reason why it's going to be quite easy is because we're only going to focus on resistors. So in the beginning here, we're going to see here is that we're going to only put this on resistors. And what I mean by that is that go look for the resistor which is going to be the controlling element. That means I'm going to have a resistor like this, and you're going to see that the controlling is going to be either the voltage across this resistor, or it's going to be the current through this resistor. And you're going to find that later on, we will include KCL nodes and KVL loops. And these can make it considerably harder. But for right now, we're going to only focus on resistors. So
Carlos?
now, yes.
When you say see how it's defined, do you mean determine if it's a resistor? Or
Yeah.
like
Yeah, typically it's going to, like in the beginning, it's going to be a resistor, but later on, you're going to see that I'm going to say, okay, let's say that you have something like this. And you might have to apply KCL to actually find the current through that guy right there. Or you may have a loop where something like this, where you have to apply KVL to get the voltage of this open. And then that open is what's really the controlling element in that circuit. So it really depends on, it can get quite more complicated. But right at the beginning, I'm not going to do that to you because you just don't have enough experience yet. So you go to see where that controlling element is at, and then go write an equation for that current or that voltage of the controlling element. So that means here that the next step here is that now you have to determine an additional equation. That defines the controlling variable. So what's that variable? It's either going to be the controlling voltage or the controlling current, one of those two. So because of this, that means this additional equation right now, it has to be this guy here. So this is going to be our only thing that we're going to be looking at. Like I said, later on, you'll have to apply KCL or KVL to actually do that. Sometimes it's useful to apply CDR or VDR to get that controlling voltage. But for right now, this is going to be that additional equation. And here's sort of like a thing of warning. Do not place the controlling element. So remember, in this case, it's a resistor into equivalent resistance calculations. By doing that, what you do here is that you lose all information. We don't want you to lose the information. We need that information in order to solve the problem. So what I have here is that I have a fairly simple one to try to get you to see the process here. So let's go look at this thing here. So here we go. So what we want to do here is that we want to determine the voltage Vx, and we want to determine the power of the 10 ohm resistor. So how do I do that? So what you're going to do here is that we want to, you can clearly see that we have a voltage controlled voltage source. And you could see that that thing is defined across the 5 ohm resistor. So the first thing that I'm going to do here is that I'm going to go in and I'm going to use that process that I was talking about. So right now, what you're seeing here is that there are two variables, right? So if I'm going to use that two-step process, what we're going to find here is that we have really two variables. We don't know the current in the circuit, and we don't know the voltage Vx. So as the circuit stands, there are two unknowns. One is the current I that flows in the circuit and the voltage Vx. But I only have one loop. If I only have one loop, that only gives me one equation and two unknowns. That's why it becomes an issue with using the dependent condition here. So here I go. So right now I see, I'm looking at this guy and I'm going to treat the voltage source as any other source here. So my first step here is that I'm going to apply simple circuits, treating the voltage controlled voltage source, which means that's the 3Vx source, as any other. So what I'm seeing here is that I have three sources here. Okay, I have three sources. Now I can pick my current direction, my loop direction in any direction. And typically a good choice of the direction that you're thinking here is to think of what you think the current is going to flow here. So the way I'm going to look at this thing is that look at that Vx here. See how that's has a polarity of plus minus. So I'm going to assume that that is the direction of the current. So that means that my path that I'm going to take as I apply this, I'm going to apply KVL in this direction. Okay, so the first thing that I'm going to do here is that I'm going to look at resistor reduction. So I'm going to apply resistor reduction. And when I look at the resistor reduction, note that there are 3 resistors in the circuit. I can't touch the 5 ohm because that's where the dependent condition is. So that I'm going to combine the 10 and the 15. So that means I really now have only 2 resistors now. I have a 25 ohm. Now note that I have 3 sources that are in series. So I'm going to combine the 3 sources here. So what I'm going to do here is that what you're seeing here is that look at the polarity of the Vx. So now I'm going to combine the 3 sources. So what I look at is I look at the polarity. And when you look at the polarity, look how this is plus, look how this is minus. Look at the 3Vx, that's plus, that's minus. So it's in the same direction. Look at the 30. I got the plus and the minus, but look at the 3 volt, it's the opposite. So that means here, I have a source now. So my net source in this case, following the polarity, I should have 3Vx, because look at that. As I go with my KVL, I hit the positive sign of the 3Vx. I hit the positive sign of the 30. And then as I come all the way around, I hit the negative of the 3 volts. So it looks like this. So in other words, I can reduce this by writing this guy as 3Vx plus 27. Now I'm going to redraw the circuit here. So as I redraw the circuit, what I really have is what? I have an equivalent circuit. My circuit then is now a dependent source that has a value of what? Of 3Vx plus 27. I have one resistor that's 25 ohms. And I have a second resistor, which is the 5 ohm resistor. And that's what my circuit is. And what I'm seeing here is that this guy is now this guy right here. So what you're seeing here, let me actually change the color of this just to make, because of something else here.
Carlos?
Yes.
Oh, sorry, quick question. Can you explain really quick how you were able to combine the 10 and 15 ohm resistor?
Because
to me, it seems like
they're in series. Everything's in series.
even though there's a source between it?
Sure.
Oh, okay.
Series elements all add.
Right.
I mean,
guess
I
was
agree
just
that I
going
can't
off.
add the voltages and the resistors, but they're still in series because they're interchangeable.
Got it. Cool. Thank you.
And then the color that we talked about here is that this was our direction of our assumed current right here. So what I'm going to do now is I'm going to apply KVL. Because I have that dependent source, I'm going to apply KVL. So now I apply KVL to get, now remember, look at so if I put in my polarities, what were my polarities? Look at this. If I see that the current is coming through the 25 ohm, that means that has to be plus and minus. So here I go. So as I go around this thing, what do I see here? Well, the first thing that I'm going to see here is that you could see that I'm going through the 25 ohm. So this is really what? Positive V 25 ohm. I come all the way around and you could see that I'm going to hit the positive. So then I'm going to get what? Plus 3Vx plus 27. And then I come all the way around. And what am I going to get? Look at that. I come up this way. And you could see that I'm going to hit the positive of the Vx. So I get positive Vx. But wait a minute. I have Ohm's law. And Ohm's law tells me that V25 must be 25 times I. And so when I put this in, I have 25I plus, now note that I can add these two guys right here, right? They're the same. So this is going to be 4Vx plus 27 equals to 0. And look at what KVL gives me. KVL tells me what? I have I, that's an unknown. Vx, that's an unknown. So therefore, I have one equation, two unknowns. And as it stands, it's impossible to solve. So what do we got to do? We have to find another equation. How do I get that other equation? Step 2. So that means we must find a second equation to solve this. And that's exactly what step 2 does. Step 2 then brings in the dependent condition. Which we call the DC. So what the DC says is it says this: the way you get the second equation is like this. Go to the controlling element. What's the controlling element? It's the 5 ohm resistor. So what we do here is that then we go to the 5 ohm resistor, and then we see how it's controlling one, the dependent voltage here. So we go to the 5 ohm, and we see here that the 5 ohm resistor is really going to be what? That's Vx. And how is Vx defined? Well, I know that there's a current running through it, and clearly it's a 5 ohm resistor. So then from Ohm's law, I write 5I. In other words, I have Vx minus 5I equals to 0. And this now gives me a second equation. And this is what I call the DC. So now what we have here that we have two equations. So now we're going to solve, right? This is equation 1. This is equation 2. We're going to solve 1 and 2 to determine Vx. So in other words, I have 25I plus 4Vx. And then I'm going to bring the minus 27 to the other side, right? That's our equation 1. And then I have, let's say, how about 5I minus Vx? And it looks like this, and that's our equation 2. So what I'm going to do, I want to get rid of what? I want to get rid of the current. So the way I'm going to get rid of the current is I'm going to do what? I'm going to multiply this by minus 5, and then I'm going to add the equations. And if I do that, you could see that when I sum these guys, I'm going to get 0 here, and this is going to be plus 5Vx. So here I'm going to get plus 5V, oops, sorry about that, 9Vx. And then on this side, I'm going to get minus 27. So in other words, this tells me that Vx must be minus 3 volts. I now know what the voltage is. So What that tells me here is that the direction of the current that we assumed is actually incorrect. The current is going to be going in the opposite direction. But that's what the voltage is right there. So let me go get that question up here and bring it down. And what you're going to see here, delivered to what? This resistor right there. So what's probably the best way to do that? We could do this any way you'd like. Probably the easiest thing to do is that because these guys are in series, we know that they all have the same current. So I need to go calculate what this current is right here. Okay, let's go do that. So from the Vx value, what we find here is that, so from Vx, we see that Vx was equal to what? 3 volts, but that should have been what? 5 times I from Ohm's law. So therefore, this tells me that the current in the circuit is actually going in the opposite direction, which is going to be this now. So now I know the current in the circuit. Since I know the current in the circuit, I could then go in and calculate the power of the 10 ohm resistor. And how am I going to calculate? It's going to be I of the 10 ohm resistor squared times the resistance of the 10 ohm resistor. So then this will be minus 3/2 squared times 10. And when I calculate this value, I get 3.6 watts for the 10 ohm resistor power. And of course, this guy's passive. That's how you deal with dependent sources in a circuit. Okay, so that was a warm-up here. So let's go get the other circuit. Okay, let's go get the other circuit. One more example on this, and then that will be the end of the chapter. So here's our last example, and it says determine the current I3. So what do we know here? Well, you can see here is that I have 3 sources that are in parallel, right? If I come in and I draw my nodes, you could see that node, and you could see this node right there. So everything's in parallel. What do we know about things that are in parallel? Well, they have the same voltage. So we all know that they have the same voltage. And what you're also seeing here is that there are 2 resistors. But what you also see here is that there are 3 sources that we can combine. So let's combine the 3 current sources. So I'm going to pick the direction. I'm going to say that because 2 of them are pointing up, what I'm going to do here is that I'm going to combine all of them. So I'm going to say that our source here is then going to be positive pointing up. So then I'm going to say, what's pointing up? I have the 3ix, I have the 4, and look at the 8. It's in the opposite direction. So I'm going to give it this guy. So it's going to be 3ix minus 8. That's what our source is. So when I look at my circuit then, since I have a dependent source there, I have to draw my dependent source with the diamond pointing up. And this guy is going to be what? It's going to be 3ix minus 4. And then I have 2 resistors in parallel. So in other words, here's my 3 ohm, here's my 2 ohm, and I see here that this guy is my Ix. So So now what I want to do here is that my goal here is that I really want to determine this current right here, I3. That's what our goal is. So the question is, I can treat this guy using simple circuits. So I'm going to treat this as any circuit here. Since I have a current source and I have two resistors in parallel, then what I'm going to do here is that I'm going to go in and actually do that. So here I go here. So now I'm going to apply CDR to get current I3 ohm. So here I go. I want the current of the I3 ohm. And this guy's going to be what? So it's got to be the opposite resistor divided by the sum. So it's got to be 2 plus 3 times the current source. And in this case here, the current source is going to be 3ix minus 4. So if I just clean this up just a tiny bit, I see that I have this guy right here. And what you're seeing here is that I have one equation that has what? Two unknowns, right? One equation with two unknowns. And what are my unknowns? There's Ix and there's I3 ohm. So those are my two unknowns. So what do I got to do here? I got to go in and I have to apply my DC condition here. So then I'm going to go to my next step here. Typically, I don't say step 2. I just say I'm going to apply my DC condition. I'm going to apply my DC, which is my dependent source condition here. So what do I got to do here? I got to go and I got to rewrite Ix to the best of my ability in terms of I3. So in other words, we want to rewrite / relate I3 ohms and Ix. So note that those are two currents right there. The fact that there are two currents, what's the easiest way to connect two currents? It's KCL. So the fact that there are two currents implies using KCL. So what I'm going to do here is that look at my node now. At my top node, you could see that I have one current going up and I have two currents down. So what I'm going to do here is that I'm going to apply. So at the red node, I'm going to apply KCL. And as I do that, you could see that the current in, right? Remember, when I say KCL, don't use a sign convention that the book is telling you. Don't mess with the signs. The current in to the red node is what? There's only one. So it's got to be in. It's going to be 3Ix minus 4. What's coming out? I3 ohm plus Ix. So this is now a new equation. This is what I would call my DC condition. And so when you're looking at this thing, if I rewrite this, I'm going to bring one of these over so that I can get a cleaner equation. So if I bring the Ix over and I bring the I3 ohm over, I'm going to get this here. I'm going to get 2Ix minus I3 ohm. And then I'm going to bring the 4 over. And so this is now my DC, which is my second equation. So now I have two equations and two unknowns. So here I go. So now I'm going to solve this. these two equations for I 3 ohm. So here I go. So the first equation reads what? Reads 2/2. So I'm going to have 2/2 3ix minus 4 equals 3I ohm. This is 1. And then 2 is going to be 2ix minus I 3 ohm equals 4. So I got to clean this up a little bit. So the way I'm going to clean this up is I'm going to do the following thing here. So, well, if I do this, I'm going to keep my I3 here, and I'm going to bring the Ix term to the other side here. So that means I'm going to have plus I3 ohm. And look at this term here. I'm focusing on this term right here. I'm going to bring it over. So I'm going to get a negative sign. And so then I'm going to get 6/5. So I'm going to get minus 6/5 Ix. And then I'm going to keep that -4 here. So I'm going to get negative 8/5. And then I have 2Ix minus I3 ohm equals to 4. So those are my two equations right there. So I got to solve these guys here. So if I solve this equation, what you're going to find here is that you're going to get that I3 ohm is 2 amps. And that's what my current is running through that 3 ohm resistor. So that concludes chapter 3 or chapter 2. Any questions before I move on? Okay, so just to make sure that we're loud and clear, we have a quiz when? Wednesday. We don't have lecture on Monday, but you have a quiz on Monday on this, and you're going to get 2 of them. You're going to get one that's resistor reduction, and you're going to primarily focus on CDR and VDR. And then you're going to get a second one with a dependent source. And that second one with the dependent source, what you're going to find here is that it's going to use these 2-step processes that we're talking about. So if we don't have any questions, then let's get started here. We are now in the next chapter, which is chapter 3. And I'm going to tell you right now, this chapter 3, you know, it's surprising. People really love this chapter. I've heard words where circuit students say, you know, this is like circuit solving is enjoyable. Like I really like doing homework, and I'm going like, I mean, you're not getting any brownie points from me just because you're telling me that you're liking solving the circuits, but it makes you feel really powerful because you're gonna take any circuit and you can apply this, and you're going like, holy shit, this stuff is so easy to do. But what you're going to see here is that there's the complexity of the circuits. They're going to get more and more challenging as we go through chapter 3. But I want to remind you also that the techniques that we're really using in chapter 2 here are actually the most important techniques in this course. And let me tell you why. The techniques that we're going to learn in chapter 3 are very powerful. And you're going to see here that they're going to be good for chapter 3, chapter 4, and sometimes they're going to be really good in chapter 5. And then you know what happens? We won't be able to use them again. How we deal with KVL and KCL is really important. And the reason why is that as soon as we get to chapter 6, we're now in nonlinear circuits. That means everything VDR, CDR, all those resistor techniques that we were using, they all disappear because that's only for linear circuits. We're going to be in nonlinear circuits. And then there's a big divide. We go from systems of equations to now differential equations. And so all this KVL and KCL comes back in a rush. And you cannot use any of these powerful theorems that we're about to use. So remember, this stuff is only good for about 2.5 chapters, and then it all disappears. And we're down to the brute force of KVL and KCL. But with practice, you'll see you'll become an expert at KVL and KCL because you're going to have to, because I'm going to keep pounding on you until you get it. So here we go. Let's go to the next chapter. Oh, by the way, before I move on, I want to remind you that even though we don't have a lab, you have a wiring PLC. Respect the PLC, okay? I'm not covering any of the material in the PLC. You have one homework problem on it, and you have the PLC, and that's the only time you're going to see it from me. Only in the PLC. And when you go to wire it, you're going to have to make up resistors to get to the Y delta resistors. You're going to have to use the resistors in your box to create that. And what you're going to find here is that you're not going to be able to create it exactly. So you're going to have uncertainties in your measurements versus your theoretical predictions. And that's okay. You just should be in the ballpark. That's the important piece. But the wiring is solid. And it's all about series and parallel, believe it or not. It may not seem like it, but it is. You could go online and you could see the derivation of the transformation. I'm not going to do it for you, but it's all about series and parallel. Okay, here we go. Next chapter. And the next chapter here is that we are in chapter 3. And chapter 3 is called Methods of Analysis. And what this really means, it's about node and mesh analysis. Oh my gosh. You're going to love this chapter. Oh my gosh. And the reason why is that circuit solving now becomes easier. And it is so powerful. And what we do here is KVL and KCL, the way they're set up in linear circuits, the way they teach it to you in Physics 4B is the worst possible way to do it. And what I want to do here is that I'm going to show you the right way to do that. So what you're going to find here is that node analysis is based in KCL, mesh analysis is based in KVL. And here's what you find. Node analysis uses KCL to find node voltages. And you got to be careful. A node voltage is a potential. So a node voltage is meaningless. So what we do here is that to calculate voltages, we have to calculate the difference in node voltages. So what this tells us here is that a voltage is equal to differences in node voltages. And that's a little bit surprising. And here's where you're going to really learn about the ground. And then we could say the thing about mesh analysis. So mesh analysis uses KVL to find these things that are called loop or mesh currents. And these loop currents are really counterintuitive. I mean, it's like really amazing that they actually exist. And by the way, when we do the lab, you're going to be measuring loop currents. And you also have a PLC where I'm going to ask you to measure loop currents. And you're going to see that these things are actually physical things, but they're, like I said, they're kind of out there. So what we want to do here is that I'm going to start off with node analysis. I think node analysis is easier to conceptualize. And then what you're going to find here is that then later, I'm going to bring in mesh analysis, which I think is harder to conceptualize. So here we go. Node analysis. And what you're going to find here is that when you look at node analysis, what we're going to do here is that we're going to bring this in a series of steps. So it turns out that it's easiest to start with only independent current sources. And then what you're going to find here is that then later we add voltage sources. And when you add voltage sources, we then start talking about something that arises that is known as a supernode. And then later, we add dependent sources, which of course makes things more complicated. So there's a three-step process. So the way I'm going to do this here is that I'm going to start with node analysis. I'm going to do independent current sources. And after I do independent current sources here, we're then going to go in and we're going to move to node analysis with voltage sources. And then I'm going to go to mesh analysis and start the same process. And then at the very end, I'm going to add dependent sources, because the dependent sources, once we're there, you'll see really add a lot of flavor to the circuits here. So here we go. So then I'm going to really talk about node analysis. With current sources only. So in order to really start talking about node analysis, what we got to do here is that we got to go back and revisit the idea of a voltage. Okay, so here's what we did. So what do we mean by a voltage? So the first thing that I should say here is, what do we mean by a voltage? Well, typically, the way we do it here is that we say that we have some plate, and let's say that this plate here is positively charged. And then we say that we have a second plate. And in this case here, we say that this plate is negatively charged. And what we say is the voltage across this thing, right? The voltage across this thing here is really the difference between the positive plate and the negative plate. And what we find here is that these guys right here, this is an arbitrary reference. Because you know that in potential energy, it's only the difference that matters. So therefore, when we talk about voltage, it's only the difference in potentials that matter. So what we do here is in the circuit, so what we're saying here is that it's, how do I say this? In node circuits, you will have to define a ground. Now, there's some, and typically you choose it the most convenient one, but you're always going to know one node voltage. So what this implies here is that you're always going to know one node voltage. And that node voltage, of course, is our 0 volt, our ground. So what this says here is that means that if you want to calculate everything in the circuit, what you're going to need here is that you're going to need to know all the node voltages. So to determine all of the voltages in the circuit, all node voltages must be calculated. And so what you find here is that I'm now going to have what? I'm going to have n nodes, but one of these nodes we're always going to know, right? And the reason why we're going to know this is because this is the ground. So what you're going to find here is that we don't need to calculate all of the nodes. We need to calculate n-1 nodes in a circuit. And that's because we know what the ground is. So in any circuit, we need to calculate n-1, not n. Yes.
Does it matter where we put the ground?
No, it's arbitrary. It's always arbitrary. And, you know, maybe I should actually make a remark about this because I think this is going to keep coming up. And so let me give you an analogy. And this is about the location of the ground. I mean, there's some locations that are better than others, but you're going to see that you're going to get so fast at these calculations that it doesn't matter. Let's think about dropping a ball, okay? So you could imagine, here's the ground, and now I have a table. And what I'm going to do here is that I'm going to drop a ball here. So you could imagine that this is the ball that I'm going to drop. Now, as I drop the ball, there's two ways that we could calculate the potential energy of that ball. One way, we could set the potential equal, we could set the ground as y equal to 0. In other words, I could set that equal to 0 there, or I could come in and I could set this guy equal to 0 at the tabletop, which tells me that I'm going to set that equal to 0. So when I look at the height change of the ball, right? So for the black, what you're seeing here is that the ball starts off from what? It starts off at some height, y1, and then what's it going to do? It's going to fall to its second location right here. So when I look at this guy, that is the height change that the ball fell to get to where? The top of the table. Right? Conservation of energy says that. Or I could do the following. I could come in here and I could say y1 is 0. And then this height from here to here is really y2 with the purple. But when I look at the potential difference here, these two guys are the exact same height change. In other words, potential choice of the ground is arbitrary. In an electric circuit, where you place the ground is arbitrary, just like you're putting this ground for the ball that's falling. Okay, I'm out of here, right? Enjoy the long weekend, right? Go shopping at Ross, do the TikTok videos, okay? Adios.
Good one, Carlos.
Okay,
Bye,
Carlos.
Carlos.
bye-bye.